Let's find the Taylor and Maclaurin series of the hyperbolic cosine. The Taylor series is defined as an infinite sum of polynomials whose coefficients are the nth derivative of the function evaluated at b, which is the base of the Taylor series expansion, and divided by n factorial. The Maclaurin series is a special case of the Taylor series, and it's when the base is 0. So setting the base of the Taylor series to 0 results in the Maclaurin series. We'll take a look at two methods to find the Taylor or Maclaurin series of the hyperbolic cosine. The first method is the more typical one. It's the standard approach of finding the Taylor series expansion for any function. The second method is using the exponential definition of the hyperbolic cosine to derive its Maclaurin series. If you're only here for the result, then I recommend you skip over to the second method because it's much quicker and more straightforward. But if you're here for a learning experience, then do take a look at the first method, because if you understand it, then you'll be able to derive the Taylor series expansion for any function. The standard method is to look at this general formula for the Taylor series and try and figure out an expression for this coefficient term in general for all values of n. The way we do this is we start with the first few terms. So in our case, when n is 0, then the 0th derivative evaluated at b is the function itself evaluated at b. So that's the hyperbolic cosine of b. And 0 factorial is just 1. When n is equal to 1, we'll take one derivative and evaluate it at b. So that'll be the hyperbolic sine of b. And we'll keep adding more terms until we figure out some sort of pattern. If we continue with n equals 2, 3, 4, and 5, we'll start to see this pattern. Notice that when n is even, we have the hyperbolic cosine of b divided by n factorial, whatever this even n is. But when n is odd, then we have the hyperbolic sine of b divided by n factorial, whatever this odd n is. This suggests that in general, for all values of n, the coefficient term of the Taylor series expansion is either the hyperbolic cosine of b over n factorial or the hyperbolic sine of b over n factorial. Now, we need to think of an expression in terms of n that'll only keep the hyperbolic cosine if n is even, and only keep the hyperbolic sine if n is odd. Usually, the term we use to achieve such an objective is something to do with -1 to the n, because we know that -1 raised to an integer power will be +1 if this power is even, or -1 if the power is odd. But this is not quite what we want. We want something to give us 1 for the evens and 0 for the odds, or 0 for the evens and 1 for the odds, depending on which one we want to keep. So let's add 1 to this -1 to the n. If we do that, then the result will be 2 for all even values of n, and 0 for all odd values of n. But we don't want 2, because then we would be changing the value. The objective is only to keep the evens and delete the odds. Then let's divide by 2 so that we get 1 if n is even and 0 if n is odd. So this is precisely what we want for the hyperbolic cosine terms. So let's place this 1 plus -1 to the n all over 2 next to the hyperbolic cosine. For the hyperbolic sine, we need something that will eliminate the evens and keep the odds. So we'll use something similar, except that we'll have a negative sign instead of a positive sign. So we'll have 1 minus -1 to the n all over 2. And that'll give us 0 for all the even ends and 1 for all the odd ends. So this is precisely what we want for terms involving the hyperbolic sine of b. Let's simplify it a little bit by bringing the n factorial to the front, and then we can add the fractions since they have the same denominator. So we now have this general expression for the nth derivative of f evaluated at b over n factorial, which is the coefficient term in the Taylor series expansion. So our f of x is the hyperbolic cosine, and now we have this general coefficient term. So all we need to do is to substitute this inside the series. And that's it. This is the Taylor series expansion of the hyperbolic cosine. If we want to find the Maclaurin series, then as we said in the beginning, we'll use a base of b equals 0. Substituting b equals 0 results in this simple series, because the hyperbolic sine of 0 will vanish, and the hyperbolic cosine of 0 is just 1. So this is the Maclaurin series. But we're not quite done, because there's some simplification we can do. Remember this 1 plus negative 1 to the n all over 2? We said this keeps only the even terms and removes everything that is odd. And we can see that very clearly if we spell out a few terms from the series. Notice that we only have x to the 0, x squared, x to the 4, x to the 6, and so on. If we look at the pattern, then the general term in this series is x to the 2n over the factorial of 2n. So this general term is precisely equal to this general term. So why not substitute x to the 2n over the factorial of 2n? Because this is a much cleaner, simpler way of expressing the general term inside the series. The final step is to find the radius of convergence. Where is this Taylor series expansion valid? To find that, we'll use the ratio test, the limit as n goes to infinity of the next term in the series divided by the current term. Substituting, we get the following limit. Now let's distribute and express x to the 2n plus 2 as x squared times x to the 2n. Doing so, we can see that x to the 2n cancels out, and then we can take the x squared outside the limit because it's independent of n. To simplify the factorials, notice that we can express the denominator as 2n plus 2 times 2n plus 1 times 2n factorial. So the 2n factorial cancels out. And we're left with the limit as n goes to infinity of 1 over some quadratic expression in terms of n. So this limit is obviously 0. We can see that it's less than 1 regardless of x, which means that the series is absolutely convergent everywhere, no matter what x is. In other words, the radius of convergence is infinity. So that's it. This is the complete Maclaurin series for the hyperbolic cosine. In the second method, we'll use the exponential definition of the hyperbolic cosine, which is e to the x plus e to the negative x all over 2. We know that the Maclaurin series of e to the x is x to the n over n factorial. And we also know that it converges everywhere, so the radius of convergence is infinity. To find the Maclaurin series for e to the negative x, all we need to do is replace x with negative x. So we can rewrite negative x to the power of n as negative 1 to the n, x to the n, and it's very easy to see why the radius of convergence is still infinity. So the series for the hyperbolic cosine will be derived by adding these two series and then dividing by 2. The radius of convergence will be infinity in the end because both of these series converge everywhere. Adding the two series, we get the following result, and now we can combine them together and factor out the x to the n term. Doing so, we get 1 plus negative 1 to the n over n factorial times x to the n. All that's left now is to divide both sides by 2, and that will give us the Maclaurin series for the hyperbolic cosine. Notice that this is the exact same general term we got using the first method. And for exactly the same reason, we can rewrite it as x to the 2n over 2n factorial. And as we said earlier, the radius of convergence is infinity.